Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. In the last session, we discussed the system reliability considering redundant subsystems, or we called it static redundancy, and we calculated, derived an expression for mean time to failure, then failure rate, and we consider it in general, that is n subsystems in parallel. And also we just started to discuss, we could not finish that one. This is the reliability if k out of n elements are necessary. So, if I consider this case, that is the n elements are in parallel. So, the failure will happen when all the elements fails, even if one element works, then this means that the system will work. But in practical situation, this does not happen. We need minimum sum of the elements to work out of this total n elements. And in the last class, we just started discussing the topic of what will be the system reliability if k elements out of a elements are operational. So, today we will continue with this, but in this system we have not considered any switching element. Now, we will consider the dynamic redundant subsystems, where we will consider this is the switching. It can be the switches at the input section, switches can be the output section. We will do it today. So, now if you remember in the last class, we said that is the reliability of k out of n elements. So, I will write it again for correct operation. For correct operation of a system of k elements out of which n elements need to perform successfully. Okay. And means that the system does not fail. So, under that condition we wrote the system reliability R of S, R S is equal to 1 minus summation of I is equal to 0 to n, then k I, this is the combination of k out of I out of k elements. So, this is R I, then 1 minus R k minus I. So, this is where we just stopped in the last session. So, this one I can write also as I is equal to k to n, then n I, then R to the power I, then 1 minus R to the power n minus I. So, here what are the assumptions? Okay. So, what are the assumptions here? The assumptions are the first point 1, each component works independently. Each element works independently. And 2 is each component has the same reliability, has the same reliability that is R. Okay. And you all of you know that what I write N and I, if I write this way. So, this implies this is the combination, that is N C I. What are the different ways you can put this this combination I and N. Okay. Now, let us explain this using an example. So, what is the example? We will consider a system which consists of two elements. Instead of n elements, we will consider two elements, and we will consider that for the both the elements are in parallel, and for the correct operation at least one element should work. So, here a system. So, here what is the system? A system, or I should write the system will work. The system will work. The system will operate under three conditions. What is the first condition? Both are performing second case is the first one fails, the second one performing. The third case is the first one is performing, the second one failed. Okay. So, under that condition I can write the system reliability. So, the system reliability R S will be equal to R square. So, where I am considering R is the reliability which are common for both the system, then the first one fails. So, I am using the reliability function f, and the second one is working. So, I will put it R, and the third case the first one is performing. So, it is R f. So, these are just the multiplication. So, I can write this as R square plus 2 R f. So, I can write this that is the system reliability R s is equal to R square plus twice F R. Now, I can write R square same, but I can write this F is equal to 1 minus R into R, and if I simplify, then I can write this is equal to 2 R minus R square. Now, if the failure rate is we just consider a constant failure rate, then I can express this reliability function in terms of the constant failure rate or hazard rate. So, I can write if the failure rate is failure rates, of course, considering the failure rate is same for both the systems, if the failure rates are constant, and equal to lambda, then I can write R s is equal to 2, then it will be e to the power lambda 2, and this one will be e to the power minus twice lambda t. Okay. Now, if I want to calculate what is the failure rate of the system failure rate, so I can calculate it by the formula which is derived in our initial sessions. So, I can calculate the failure rate by using the formula. So, failure rate of the system So, I can write lambda s is equal to f t by R s. Okay. So, so lambda s, this already we did earlier. So, lambda s is equal to f t by R t, and then I can write this is equal to minus R dash t by. So, I should write this is as f s, I will write it R dash hat divided by R dash t. So, f s t is the probability density function of the failure, that is the failure of the overall system. So, that is why I am writing f s t is equal to, then it will be minus R s t, that is the derivative of R s t divided by R s t, and then I can substitute those value those expression. So, first I will write in the denominator. So, denominator the expression was 2 e to the power minus lambda t, then it was minus e to the power minus 2 lambda t. So, this is now I am to derive this and put it into the numerator. So, if I derive this, so it will be, and a minus sign is there in front of it. So, this is equal to minus. So, this is equal to minus 2 lambda e to the power minus lambda t, then it will be plus, because already a minus sign is there, and if I take a derivative of this. So, both the minus and minus will become plus. So, I write 2 lambda e to the power minus twice lambda t. So, if I now simplify, then I can write this expression is equal to 2 lambda, I can take it out. So, inside the bracket it will be e to the power minus lambda t plus 2 plus, no, now it will be minus sign will be there inside, because this minus sign will come this. So, minus e to the power minus twice lambda t, okay. And then the denominator will be the same. So, e to the power minus lambda t, then minus e to the power minus twice lambda t. Okay. Now, further simplification we can do algebraic simplification, and I can write this is equal to 2 lambda 1 minus e to the power minus lambda t divided by 2 minus e to the power minus twice lambda t. So, this is the failure rate of the system failure rate, and you see the system failure rate is not constant, but it is a function of time. Okay. So, now we will consider a case that is a dynamic redundancy with switching. So, we are considering two cases. We will today will discuss this. So, if you see here, there are two systems in parallel and there is a switch. So, switch can connect to, it can connect to this circuit, can connect to this circuit or connect to this circuit, and this is the active or primary. This is active or also called primary. This is the redundant one or the redundant one or backup. So, the concept is like that. Suppose this active one fails, so automatically the switch will come to this position and this switch will also come to this position. So, this will come here, this will also come here, and this will start operating. Okay. But what is needed here? Here now this element, the switch element also has become a part of the reliability, because if the switch does not work, okay, if that it should go either to this point, it should either to be connected to this point or to this point. If it does not occur, then the system will not work. So I will just write down this thing. So, what is our intention now? Intention to find out the system reliability. So, what we will do? We will consider first this one, then we will do this one in the next lecture session. So, in order to derive the system reliability, function for a system having dynamic redundancy with switching capability. So, we will assume a few points to simplify our the first cut the derivation of the system reliability. So, we will assume, let us assume that point number 1. So, we will consider two units, one active, as I already written, one is active, means it is operating successfully, active or primary. Okay. Second, one standby, or redundant or backup. So, this is what is the second point. I think better to go to the next slide. Yeah. So, the second point is the switching mechanism. The switching mechanism is perfect. So, here we are considering there is that the probability function of the switches is equal to 1, means the failure is 0. Switching mechanism perfect. What does it mean? That is, it always works. It always works without failure. Means the reliability of switch is equal to 1. Okay. Now, further we will assume that the failure times that is the random process, the failure times of the components or the elements follow exponential distribution. exponential distribution. What does it mean? That it means the number of failures in time t follows a Poisson process given by, you can give, it is given by p k is equal to lambda t k by k factorial multiplied by e to the power minus lambda t. Okay. Go further, let t is the mission time, that is the mission time to failure, mission So, here failure follow a Poisson distribution, with rate, with failure rate lambda. So, the probability that a component survives time t, that is p, no failure in time t. So, I can write is e to the power minus lambda t, that. So, this is basically R t, this one is basically R t. Now, the primary unit, now let us write down the primary unit works without failure until time t, So, this is p 1 t is equal to e to the minus lambda t. So, this we will write equation number 1. Now, let us assume that the primary fails at tau, and when it fails up, so switch will be, the switch will go to the input of the backup system. So, the backup should survive, survives the remaining period, t minus tau. So, it will basically this is small t. Okay. So, it will be t minus tau. Okay. Now, let us assume that the failure of the primary element works at time t. So, I can write tau now it will belong to this interval 0 to t, then the probability of the primary fails at the time tau will be given by just what you have to do, you have to differentiate the probability function, that is e to the lambda t. So, if I do that d by dt, and if I can put then I will let me put e to the minus lambda t, then multiplied by d of tau. So, this will give me lambda e to the power minus lambda tau and d of tau, and here I am doing t is equal to tau. So, we will proceed further. In fact, we need to now find the probability that the backup element will work successfully from the time t to t minus tau to t. So, that we need to do, and finally, we have to derive an expression for the system reliability. Okay, thank you very much.